In this example, let's give you a little bit of a more challenging version of this type of problem where we're finding the absolute maximum and absolute minimums of these following functions. And since we have an interval, that it's a guarantee, as long as the graph is continuous, we're doing this extreme value theorem. And as long as it's continuous, we will have an absolute maximum and an absolute minimum. Right? We just have to figure it out. So we have some sort of an equation. I don't have any domain issues because I'm cube rooting. Cube rooting, you can cube root anything, positives, negatives, zeros, anything. So we don't have any domain issues, and we're going to be going from -1 to 2. So we're going to find critical values, which is us taking the derivative, setting it equal to 0, and we're trying to figure out where we have slopes at 0, right? So those are kind of our situations that can happen with that. So let's kind of put all this together. So let's start off with, how do I want to do this derivative? So I can do a product rule on this, but I think it might be easier if I distribute this in. And I have a power of 1 on here. So if I distribute that in, I'm going to have a 2x to the 2/3. And I'm going to have, let's see, minus, and then if I have this, I'm going to be taking the power, I'm going to be adding those exponents together. So I have a 3/2 plus a 3/3 plus a 2/3 is an x to the 5/3. All right, and I think that's easier to do my derivative. If I have the opportunity to distribute and it's reasonable, I would take this approach to do my derivative versus doing a product rule. Just might be a little bit smoother. So let's do our derivative. So if we do the derivative, we're going to take 2/3 times 2, which is going to be 4/3. We'll subtract 1, which is a -1/3, minus 5/3 x, and then we'll subtract 1 is going to give us a 2/3. All right, so at this point, we need to do a little bit of manipulation, right? And so I need to show you to manipulate this. We're going to take this thing and rewrite it and kind of clump it all together. It's kind of a mess right now. So I had some little space over here that I'm going to redo. Okay, so I'm going to take this original problem that is 4b, and I have 4/3 x to the negative. This negative power I'm going to rewrite, and I'm going to bring it down to the denominator. So I'm going to join the 3 that's already there. So I have 4, and then it's going to be 3x to the positive 1/3 power. All right, so there's the first piece. And then this next piece is, I'm just going to write this as a fraction. This is a positive exponent, so I'm going to clump it together with the 5. So it's going to be a minus 5 x to the 2/3 over 3. All right, so I want to put all this together, so I have one fraction. So in order to do that, I need a common denominator. They already both have 3's, but I don't have an x to the 1/3. So I'm going to multiply an x to the 1/3 to both. Okay, so that's going to give me, not changing anything on this one. And then over here, I'm going to have a common denominator of 3x to the 1/3. And then over here, we're going to add these exponents together. So 2/3 plus 1/3 is going to give me a 1. So that actually cleans that up very nicely and just makes it a -5x, which allows me to pull this together, 4 minus 5x over my common denominator of 3x to the 1/3. All right, so that's back down to here. So 4 minus 5x over 3x to the 1/3. All right, so there's my derivative. So at this point, we need to set it equal to 0, but there's actually 2 scenarios I need to consider. So when we take this and set this equal to 0, that's fine, but there's also a potential for an undefined because we have a domain issue. So we're going to do 2 different things. So we want to figure out when our derivative is equal to 0 or when it is undefined. Right? That's kind of our goal. So we are going to take this equation, 4 minus 5x over 3x to the 1/3, and set it equal to 0. And I'm going to make it a fraction. And so when I set it equal to 0, I'm really just setting the numerator equal to 0. Because if you cross multiply this to get rid of your fraction, this cross product is going to go away, and this is just going to equal itself. So really, it's just the numerator set equal to 0. So 4 minus 5x equals 0. And if I solve that, I would subtract 4 and divide by 5, -5. So I'd have a -4 divided by a -5. So that would be a positive 4/5. So there's one critical number. And then my other one is the fact that my denominator, my 3x to the 1/3, has a potential to equal 0, which is bad. So I don't want that to happen. So I have a value that I need to kick out. I have an undefined slope. So I divide by 3 and cube it. So I have an undefined slope at x equals 0. All right, so now let's do the last piece of this. And the last piece of this is, let's plug in all of our stuff. So we have f of -1. We're going to plug in all of our critical numbers. We have f of 0. We have f at 4/5. We have f at 2. So again, now that we have all these values, we can just plug them in. And if we plug in -1 into this equation, that gets us positive 3. If we plug in 0, we get 0. We plug in 4/5, we would get approximately 1.03. And then if we plug in 2, we would get 0. So without looking at the graph from this interval on this graph, that we would have a high point at 3. That's the highest value. So we're looking at an absolute max. Oops. Max. Ran out of space. Absolute max. And then we have a matching zeros. So we have an absolute max. We have matching absolute mins. All right, so let's take a look at the visual of what this thing actually looks like and make sure all of this makes sense. So again, once we did all of this stuff, we took our derivative, we set it equal to 0. Here's us setting it equal to 0. That gave us a critical value of this, but we also have a domain issue. And so we were undefined at 0. So we're going to take a look at what all this stuff means and looks like. All right, so let's shift over to Desmos. All right, so here is our graph, and we have it limited from -1 to +2. And here's our graph. So here's our high point at -1. That gave us a y value of 3. And then we have low values of 0 and at 2, right? So these y values are 0. And so there's where when we set the derivative equal to 0, and we had that domain issue, we have an undefined slope because it goes vertical at that one spot. Everywhere else is okay, but that's not differentiable, so that's a bit of a problem. But as far as a high and low point, we didn't care. We were just going to have to still use that value because there wasn't a break in the graph. It just, we had a problem with the slope at that point, not necessarily the whole graph. So that is us. Go back to the original. That was us finding this, some maxes and mins on some sort of an interval on a little bit more complicated equation.